Virtual machines are so ubiquitous that many people hardly notice them. They're just part of the IT landscape. So, to really understand and appreciate machine virtualization, it helps to consider a world without virtual machines. Without machine virtualization, programs run directly on the host, specifically on the host operating system. For example, you have a laptop running Linux or Windows, and you run programs on it, like a web browser or an email client, for example. This is what we call running applications natively, or just native computing. We are running them directly on the host operating system. What this means is that those programs have full access to the host's resources, CPU, storage, memory, networking, etc., via the host OS. The host OS abstracts the host hardware so applications can use it. The thing to notice here is that the host can run only one operating system at a time. But what if you want to run different operating systems simultaneously, or perhaps you want to run multiple instances of a certain OS? This is where the need for virtualization comes in. When you implement machine virtualization, applications run inside of a virtual machine, a VM. Specifically, they run on a guest OS, which runs inside the VM. What's cool about this is that multiple VMs can share the host hardware, CPU, memory, storage, and networking. Again, the programs running in a VM have access only to the host resources that are allocated to the VM. For example, if only 8 gigabytes of memory are allocated to a VM, then that guest OS and the applications running on it can only ever use a maximum of 8 gigabytes. As another example, if a VM is given a virtual disk or a vDisk that's 1 terabyte, then that VM cannot consume more than that amount of space on the host's storage. Also, VMs are isolated from each other. One VM cannot read the memory of another VM, for example. Also, a single host can run multiple VMs and by extension, multiple operating systems. Now, earlier I promised to give you a more rigorous definition of a virtual machine, so here it is. A VM is an efficient, isolated duplicate of the real or physical machine. This definition actually comes from a paper published in 1974. Wow, okay. Virtual machines are not a new concept by a long shot. It just took a long time for the technology to catch up to the theory. Now we need to break this down a bit. Think about what a VM does. It runs programs, which are just collections of CPU instructions. The word efficient here means that the VM is actually directly executing those instructions on a real physical processor. The VM gets direct access to the physical CPU, albeit with some exceptions. And that's important because having that access, a program running in a VM can perform just as well as one running outside of a VM. Again, this goes back to that idea of virtual, meaning strength or power. The VM has the power of the real CPU at its disposal. Having said that, the word isolated means that a VM can access only the resources that are allocated to it. It cannot, for example, reboot the host machine or format its hard drive, thankfully. The VM only has access to a specific subset of the host's resources. The control program that creates the VMs is called the hypervisor. Originally, it was called a virtual machine monitor or VMM, and you will still sometimes see that terminology. The hypervisor is responsible for allocating resources to the VM. It's actually what controls just how isolated a VM is, what host resources it does and does not have access to. Now we have to get a bit technical here. Around 1973, Robert Goldberg classified hypervisors into 2 different types, Type 1 and Type 2. This has led to a lot of unfortunate and unnecessary confusion and consternation because the definitions Goldberg provided do not match the way people use these terms today. Some of the commonly accepted distinctions between Type 1 and Type 2 hypervisors are, quite frankly, nonsense, but they are so common that they might actually show up on an exam on which you will be expected to give the wrong answer. So as much as I hate to do this, I'm going to give you both the right and wrong definitions for these terms. Ready? Goldberg said that in a Type 1 virtual computer system, the VMM or hypervisor on a bare machine must perform the system scheduling and real resource allocation. If you look up the definition of an operating system, it's exactly that. The OS performs scheduling and resource allocation. A Type 1 hypervisor is simply an operating system with an embedded virtual machine monitor. The key here is that the hypervisor and the operating system are inseparable. Put another way, Type 1 hypervisors do not ship separately from the operating system. You cannot just install the hypervisor component on top of Linux or some other OS. It includes an operating system and you have to use it. VMware's ESXi is a good example of this. You have to install it directly on the server hardware, what people call installing it on bare metal. Now let's contrast Goldberg's definition of a Type 1 hypervisor with the way people use the term today. In modern times, people consider a Type 1 hypervisor one that's designed for running VMs on server hardware. It's really geared towards server virtualization. Type 1 hypervisors don't come with a fancy GUI interface. If you've ever installed any of these, you know what I'm talking about. People often consider KVM and Xen to be Type 1, when in reality, they're just standalone hypervisors and do not perform operating system functions. In fact, if you want to use Xen or KVM, guess what? You have to install Linux first. If the hypervisor is bundled with an OS, as in the case of Hyper-V, the OS is generally going to be stripped down and customized so as to allow for efficient use of the host hardware. All right, what about Type 2 hypervisors? Mr. Goldberg says in a Type 2 VCS, the operating system does the normal system resource allocation and provides a standard extended machine environment. The VMM program runs on the extended machine and produces a pseudo hardware environment. Of course, clear as mud, right? What does this mean? Well, what he's saying here is that you have an operating system running on the host like you would in a native computing environment. There's nothing special about it. It is just a regular OS. Think Linux or Windows or Mac OS. Running on top of the OS is the virtual machine monitor, the VMM or the hypervisor. A Type 2 hypervisor just runs on top of the OS as a normal application. This means that the hypervisor is at the mercy of the host OS when it comes to the resources it can allocate to VMs. Some examples are Oracle VirtualBox, Parallels, and VMware Fusion and Workstation Pro. What all these have in common is that they are not integrated with an OS. They are simply applications that run on top of an OS, and typically it's a consumer OS like a Windows non-server edition or Mac OS. Think of a Type 2 hypervisor as virtualization for the masses, all the people. It's designed for personal computers, not servers. Consequently, Type 2s tend to have a robust, user-friendly interface that makes it easy to create and interact with VMs. Okay, this all makes sense, but how do you decide whether to use a Type 1 or Type 2 hypervisor? Well, Mr. Goldberg has some advice for us on this as well. If there's a single preferred operating system and a user may only need to occasionally run programs on a different OS, then a Type 2 hypervisor might be a good choice. Think of software developers who do all their programming on one machine, but may need to test their software in a variety of different environments. Perfect use case for Type 2. On the other hand, if you need to regularly run applications on different operating systems, let's say you need to run applications on both Linux and Windows Server, then Type 1 makes more sense. Kudos to Robert Goldberg for writing that paper, because otherwise we would all be a confused mess right now. Now, before we move on, there's something vitally important I want you to remember about virtualization in general, not just machine virtualization. Ready? Virtualization always adds complexity. It never makes things simpler. That's because virtualizing any system requires decoupling some of its components and then shimming another one in between. In the case of machine virtualization, we are inserting a hypervisor between the host OS and the applications that we want to run inside a VM. This is necessary because the hypervisor is the go-between that determines what host resources a VM has access to, and it also provides isolation among VMs. The point of virtualization is to improve scalability and flexibility and allow more efficient use of resources, but it is not to make things simpler.